It's important to point out that every chemical or physical process has an enthalpy change associated with it. And through calorimetry experiments, the enthalpy change values for a lot of these processes has been determined and cataloged. So what we mean by a physical process is something like a phase change. Water freezing or melting or vaporizing. So if you can imagine an ice cube melting on a hot day, or liquid water being converted to water vapor as a tea kettle steams, these are physical changes. Chemical bonds in molecules aren't being broken, just the attractive forces that operate between molecules that hold them together in different phases are being broken. So if you're talking about a phase change like melting, freezing, vaporizing, these all have enthalpies associated with them. Another way of saying that is if we want to melt ice or boiled water, we need to put heat into the system to accomplish that phase change. That might seem really obvious on the surface, but it actually has important implications for how melting or boiling work. And while they're important on Earth for understanding how to correctly engineer a system, if you want to build something like an internal combustion engine, they're even more important to understand how these types of phase changes work in high pressure or low pressure environments like under the ocean or in outer space, where you have very different atmospheric conditions, atmospheric pressure conditions, compared to what we experience close to sea level on the surface of the Earth. So we want to highlight some of these enthalpy changes that are associated with phase changes. We're not going to do too much with these this chapter other than to point out that even physical processes like melting or boiling have enthalpy changes associated with them, but they're going to turn out to be more important in a couple of chapters when we start talking about phases of matter and the properties of solutions, what we call colligative properties. So we're going to start with a specific enthalpy associated with a phase change, and we call it the enthalpy of fusion. Fusion is an old-fashioned term for melting. And so an enthalpy of fusion is an enthalpy change that's associated with the physical process of melting any solid into its liquid form. So we're going to stick with an example where we look at Earth's favorite chemical, water, and talk about the melting of an ice cube. But an enthalpy of fusion would apply to the melting of any solid phase of matter. So if you're trying to melt steel or iron and make it a molten metal, that would also have an enthalpy change associated with it, and we would call that an enthalpy of fusion. So in this case, fusion is just an indication that we're talking about a phase change from solid to liquid. You could also call it an enthalpy of melting if that's easier to keep straight in your head. But if you see it in a table, remember that fusion equals melting. So let's do a thought experiment where we melt an ice cube by heating it. Sit down and think about for a second what that would look like, and specifically try to imagine what that would look like if we could kind of see the heat energy going into the ice cube and look at how it melts. The first thing to remember is that on the Celsius scale, your ice cube is going to melt at 0 degrees Celsius. That's the normal melting point of water. So our ice cube should start out a little bit below 0 degrees Celsius, and we're going to start to warm it up, which is another way of saying put some heat energy into it. In response, the temperature of the ice cube begins to rise, and using the calorimetry equation, we could predict how much heat we have to put into an ice cube to raise the temperature by X number of degrees. We know that putting enough heat energy, raising the temperature of the ice cube enough, will eventually cause the ice cube to melt. But the weird thing is, right at the melting point, once we get the ice cube up to 0 degrees Celsius, there's a period of time where putting more heat energy into the ice cube causes it to melt, but it doesn't actually change the temperature of the melting ice any further. But after a period of time where we're putting heat energy in and melting is occurring, then if we continue to heat the liquid water, the temperature starts to go up again. And so what we end up with is this plateau region where while we were putting heat energy into the ice cube and it was actually melting, its temperature wasn't changing. And that's actually the amount of energy required to melt the ice cube itself, which we call the enthalpy of fusion. So the enthalpy of fusion is the amount of energy required just to melt the water without raising its temperature. So it's the amount of extra energy you have to put in after you hit the melting temperature of water to actually get it to melt before the water is fully liquid and the temperature of the liquid water starts to rise again. That heat input is the enthalpy of fusion. And we abbreviate that under standard conditions, delta H naught for enthalpy under standard conditions, and then a subscript to describe what phase change we're talking about. So if we're talking about an enthalpy of fusion, we would call it delta H naught fuzz under standard conditions. And every phase change for every form of matter would have similar enthalpies associated with it. So enthalpy of fusion applies to anything melting. For water, the enthalpy of fusion is 6.01 kilojoules per mole when you're going from solid water to liquid water. Enthalpy of vaporization is the energy required to get your liquid to go from the liquid phase to the vapor phase to get it to boil without changing the temperature once you've already reached the boiling point. So the enthalpy of vaporization, if we're thinking about water, is now we'd have liquid water, we put heat in and we raise its temperature up to 100 degrees. At 100 degrees, assuming 1 atmosphere of external pressure, the water will start to boil, but there'll be a period of time where we're putting more heat energy in and the water starts to boil, but its temperature doesn't change. And that amount of heat energy input is the enthalpy of vaporization. For water, delta H naught vap is 40.7 kilojoules per mole. There are other weird phase changes out there that we'll introduce you to when we talk about phase diagrams, one of which is sublimation, which you might be familiar with. Sublimation is a solid going directly into the vapor phase. So solid going directly to the gas without passing through the liquid state in between. And you've all likely seen a phase of matter that can do this. Dry ice is solid carbon dioxide, and at room temperature and normal atmospheric pressure, dry ice sublimes. The solid converts directly into the gas phase. And a phase change like that also has an enthalpy associated with it. Delta H naught sub for water, the enthalpy of sublimation, is 46.7 kilojoules per mole. Now notice that for all these phase changes, these are all positive enthalpy values. So these are all endothermic phase change enthalpies. Not every pure material or pure substance has to have an endothermic phase change enthalpy. The delta H's for phase changes when you're going to more disordered states of matter, solid to liquid to gas, tend to be positive. And then to go the other way, gas to liquid to solid, the enthalpies of your phase change enthalpies would tend to be negative. However, that's not necessarily going to be the case for every phase of matter.